So today we're going to be talking about cameras and views and viewports, all sorts of different ways that we can look into the worlds that we're creating in these games. And just to give us a bit more context into where we are in the course, so in the last lecture, there were a number of reasons that I couldn't make that lecture. I sincerely apologize for that, but the video is just as good. So the raycasting and line intersection, that will be necessary for assignment 4. So we talked about that. Now we're going to talk about cameras and views. This will be necessary for assignment 4 to a lesser extent, but it will be very necessary for the project. And then I did have caching and memory pooling right here before assignment 4, but I switched this because game tools, drag and drop, that's going to be talking about the level editor stuff. And if you do want to do the level editor for example, for assignment 4, to get some bonus marks as well as get that out of the way for the project, then I wanted to talk about that before assignment 4 rather than after assignment 4. So I just made some slight changes there. And next Thursday, so 1 week from today, is when assignment 3 is due. And I'm very pleased to be getting all these questions about assignment 3. It means that people have started it early and they're going to finish it on time. So I'm really happy that I'm getting a bunch of questions, and it sounds like a bunch of people are like almost done. So that's great that you had 3 weeks to do something and finished it in 2 or are almost done. That's awesome. Okay, so what I'm going to be doing is I'm going to be showing PowerPoint slides as normal, as well as parts of 2 YouTube videos. So there are 3 YouTube videos in this lecture. I'm going to be showing about half of 2 of them and none of another one. So this lecture is not super long. It's going to take maybe like 55 minutes to an hour. So please take that extra time later on to just make sure you watch all 3 of those videos, because it has stuff to do with like animations, cameras, views, viewports, and stuff like that that will be very helpful for ideas when you go to make your project. So please take those and watch them. So lecture number 14, cameras and views. So when we talk about video games, you know, we've got this game world with stuff happening in it, and we really do have to visualize that somehow. We've got to be able to display that information or a subset of that information to the user. And so video game worlds are often much bigger than we can display on the screen all at once. And so just like the real world, you can't see it all at any given time, right? So we can only display a subsection of the world at any given time. Now that isn't always true. Like in assignment 1 and assignment 2, we saw the entire game world when we were looking at the screen. And so what happened in those game worlds, especially assignment 2, is that whenever we positioned something in the game world, we were actually positioning it on the window as well. So in that game, there was a one-to-one mapping of things or coordinates in the game world and coordinates in the screen world. Right? And so those are 2 completely different things, and we're starting to get a taste for that in assignment 3, where you see you can run to the right, and then you can no longer see the things that were back to the left, and there are parts of the level that are over to the right that you can't see until you get there. And so we'll talk about how that happened in assignment 3. So for assignment 3, that was pretty simple, but in future assignments and in the project, it'll be a bit more complicated. So the part of the game world that we can currently see is called a view. So we're going to define this thing called a view, and that's the subsection of our game world that we can see. So to mathematically describe our desired view of the game world, we can often use the concept of an in-game camera. And that is completely, almost one-to-one analogous with a real-world camera, right? So if I take a camera and I point it somewhere, I can only see a part of the world. And then when I take a picture, then I get a 2D representation of what I see in this 3D world. And the exact same thing is happening just with, simulated physics instead of real light physics. So intuitively, we can define the location of the camera in the world and where it points, right? So when I take an actual picture, let's say I wanted to take a picture that kind of got the whole class from a little bit above, then I could say, okay, the camera is in like 0, 0, 0 in this 3D coordinate space, and it's pointing down and to the right a little bit. So I can define where the camera is. So similar to real photography, that will determine the final view of what we see. Now, an actual view has a few more parameters in it, so I can define where the camera is and where it's pointing, but maybe also some parameters of the camera, like how big is the field of view of the camera, right? So if it's a lesser field of view, then I'm sort of zoomed in. If it's a bigger field of view, then I'm sort of zoomed out. And so this would be equivalent to like the focal length of a camera if you do actual photography. So here is a video. I'm not going to play any of this video, but I do recommend you go and watch that. So you should be able to just click the link off the PDF, and I'll also include all the links in a comment in the video when I post it. So please watch that video called The Challenge of Cameras. It's an excellent video. Oh, I was going to play it there, but I don't want to play it all. I don't want to like freeboot everyone else's YouTube videos. So what I just talked about, I like talking about this in the context of 3D games first, because it's almost easier to explain the idea of a camera in 3D space because we're so used to that in the real world before I talk about 2D space. And so in a 3D coordinate system, we would just have an extra coordinate, right? So in 2D, we're talking about a flat plane, but 3D is like the actual space that we're living in. So we would define a location for our camera. So we would define the X, Y, and Z point of that camera. And then you can say, okay, maybe I want to look at this duck in the scene, right? So this rubber duck over here. And so we could do all sorts of different camera tricks to maybe follow the duck around, or, you know, you could have like a security camera type view that's just up in the top corner, etc. And so what we would do typically in a 3D game is we would define the location of the camera and then this other vector, and that vector, for example, in 3JS would be the look at vector. So you've got the position and the look at vector. So if I've got a camera up here and the look at vector, that will define where I'm looking with that camera. So what we can get from this are a number of different types of camera views, right? So these camera views, I'm calling them types. They might be called something else in other literature. So from left to right here, this would be, this type of camera here is like a fixed position following camera. So what we have here is that the camera is fixed in space, but it is constantly pointing at this object in the scene, and as the object moves around, the camera will follow that. Here we've got the typical sort of third-person shooter type camera, where it's like an over-the-shoulder following camera, where, you know, let's say, you know, I've got a camera back here always following me around, and so it can sort of see the back of my head, and as I'm moving around, the camera look at position the position is always going to be the same relative to me, but it's moving around in the 3D space, and it's always looking in a direction that goes from its position forward to the front of me. Up here, I've got just a fixed position, fixed view camera. So this is sort of that security camera type thing where it's just up in, you know, it's just sitting there always looking at the same type of thing. And down here with the advent of virtual reality and like these head-mounted displays and stuff, you've got these cameras that could be arbitrarily pointing anywhere, and just like this head tracking or eye tracking or whatever it's doing is defining where the camera is looking at and where it's positioned in the world. So in 3D, we can have so many different types of cameras, and I'm sure you can think about a bunch of different cameras that you've seen in different games, right? You might have you know, cameras that look at the front of the player so you can see what's behind you. You can think of having a rear view mirror in a driving game or something like that. So you may think, oh, well, you know, I've played 3D games. There's not really that many types of cameras. You might have like half a different types of cameras or views or whatever. So like 2D cameras and views must be kind of boring. But it turns out there's almost more options in 2D games than there are in 3D games. Not in terms of how the camera works, because yes, the camera is sort of fixed, but how we actually view into the game is, you'll see, there's a lot of options. So a 2D game camera is sort of like this. If you take our whole game world and picture that you've printed it on like a big sheet of paper and put that on the wall, right? Then the camera is always going to be perpendicular to that plane looking at it. Now, it doesn't always have to be perpendicular. It's possible that you may come up with some game mechanic where the world might look like it's tilting a little bit, but for the most part, your 2D game cameras are going to be a perpendicular camera that is pointing at the game world, right? And what we're going to do is we are going to define not the position of the camera, because that doesn't really make sense in terms of a 2D game. What we're going to do instead is define this view. And the view is essentially a sub-rectangle of the world that we're going to look at. Okay, so we're going to find this rectangle of the world that we can see. But keep in mind this analogy for a camera following us around. And the camera, believe it or not, and we'll get into this when after I play a bit of the next video, the camera can actually have far more uses than just looking at things. So for example, over here, this is an example of the camera sort of telling the player where to go or uncovering a secret in the level or something like that. So you might have something in your game where as you get sort of close to this treasure chest, the game wants to give you a little nudge in the right direction. And so the camera might just zoom out a little bit to include the treasure chest. And so there's like really interesting game mechanics and gameplay ideas that can go into cameras as well, outside of just, okay, this is what you're looking at. So I'm going to play a little bit of this video, which is about 2D camera types, and that's going to give some information. And then I have a bunch of slides which go into more detail about, or more examples of different camera types. So I'm going to play this. It does have some music. I'm going to turn that down because the music isn't super important. I think the music will be on the recorded video, but I'm not 100% sure. So let's play a bit of this video. And this is all about 2D camera types. And you will start to see from this video just a bit of the depth of that you can go into with cameras and views in 2D games. And so it's crazy, you know, most people in here have played a bunch of games like that. And if you're anything like me, I'd never even thought about the camera. Like, you know, oh, this game just plays well, right? I didn't think about, oh, there's a box there that's following, the camera is following this box instead of the player, or, you know, it never even came to my mind. And so this cameras and views, it's a necessary thing to do correctly, but it's almost like it's so underappreciated because if you do it correctly, no one even notices, right? It's just one of these things. It's like a kind of infrastructure on the road or something like that out there. You know, people only notice the potholes. They don't notice how well the road is constructed. So you kind of have this expectation of being able to play and see things properly and only really, you know, complain if there's something wrong. And it turns out, in my opinion, it's really interesting. There are a lot more camera types than what was just shown, and I'll give some examples. But it's almost like 3D cameras are easier because we live in a 3D world. And so we're used to a 3D camera all the time. So if you play a 3D game, there might be those few different types of 3D cameras that we saw. But because a 2D world is so much different than the world we live in, and the gameplay of a 2D game is so much different than what we actually do in real life, that there kind of have to be more different types of views into that world than we have in a 3D world. It's like this weird thing that's almost like the opposite of what you would think. And so we'll talk about SFML Views now because that's the library that we're using. And if you use any other 2D game library, I'm sure there'll be some equivalent of this, this view system. And so a view is literally a window into another world. It is the window in which we view it. Like if you look at that window over there, that is a literal window into the world that's outside this place, right? So if that outside this room was our game world, then we are going to define the properties of that window that let us see through it into part of our game world. And so an SF view is a rectangle representing essentially a 2D camera that you can use to specify which pixels of a game that will be drawn to the window. And so changing the window's view does not alter the underlying entity or sprite positions. It simply changes where in the window that they're drawn. So let's take a second to think about something. Up until this point, if you didn't know what an SFML view was or a camera was or anything like that, and you wanted to implement some sort of side-scrolling view, one of the things you might actually do is say, okay, let's say I want the camera to move to the right. But if I didn't have a view or a camera or whatever in my graphics engine, how might I accomplish a camera moving to the right? Well, I could move everything to the left, right? So if I actually took the positions of everything in the world and moved them to the left in the game world, that could be used to simulate the effect of a camera moving to the right, right? If you've ever been like on a train or a bus or something like that, and then something moves outside the bus, like if two buses are like together, like side by side, and the bus next to you moves, it almost feels like you're moving backwards, right? Because you see that thing moving forward, so you must be moving backward. And so it's the same kind of thing. You could simulate a camera by actually moving the things in the world, but that is a hugely complex operation, right? Think of all the entities and stuff that you could have in the world. You'd rather be able to just see a different part of the world than move everything in the world to simulate that. So by changing our view, we can change what part of our game world is shown to the player. And we saw that that's not only changing the view, but it could also implement different game mechanics and effects and stuff like this. So here I've got this. This is from the SFML tutorial. This link up here in the top right is for the version 2.5 of SFML, but it's identical for 2.6. I just didn't bother changing it. And so you've got a render window. That's what we're using. That's the type of window that we can render to in SFML. And then that window has a view. And if you don't specify a view, then it has a default view. And that default view, by default, is just the size of the window, right? So if we've got a window that's like 1920 by 1080, so you've got like a 1080p window, then that would show you the subsection of the game world between 00 in the top left and 1920, 1080 in the bottom right. And so by default, the view of a window is showing the part of the game world that's just equivalent to the size of the window. But if we want to, we could initialize the view to a rectangle located at 100, 100 with a size of 400, 200. And so what we're going to do is we're going to define a float rect. And so this is a rectangle of floating point numbers. The first two arguments are the x and y position, and the second two arguments are the width and the height. And so that's just one way to set this view. And so we can rotate it. We can set a viewport. I'll talk about viewports in a little bit. And then we could apply it to the window. So what you can do is you can create a new view. You can specify the geometry of that view, and then tell the window to actually use that view. And that's the way that we're going to do it. Then you draw some stuff, and then let's say that something that you're probably going to be doing for the project, for example, is you've got a view into your world, and then so you want to render this, you know, the things in your world relative to this window, but then you might have something like the user interface. Or like, let's say I want my hit points to always be drawn. I want to draw a little heart and the amount of hit points that I have in the bottom center of the screen, like in a first-person shooter like Doom or Quake or something like that, right? So there's some things that you do want to be in the game world, like at a position in the world that is affected by the camera, and there are some things that you do not want to be affected like that, like parts of the user interface. So if you say just draw a heart and some text, well then by default that's going to be drawn with the view of your window, and so that may actually be relative to the world position. So one thing that this is doing that you can do is you can say, hey window, set the view back to the default view. And then after I do that, I can draw some more things, and those things will be drawn with respect to the window's coordinates rather than the world's coordinates. Okay? So if I want some things to be fixed on the screen rather than fixed in the world, this is sort of the way that you do it. So you define the world viewport, you define the world view, then draw your stuff. So that draws all the game objects in the game world. Then you set the Windows view back to the default view, and then anything you draw after that is going to be relative to the window position instead of the world position. Okay? So that's how you can accomplish that. Now, I've got a bunch of slides coming up with a bunch of GIFs and images, and that comes from this article, which is absolutely amazing. It's very thorough, very well done, and so I recommend reading this article as well. And it is called The Theory and Practice of Cameras in Side Scrollers. And so side scrollers are like platforming games where it's sort of a side view of the world, and that's like your standard Mario, Mega Man, every 2D platformer that you've ever made. There are more examples of cameras and views that are not in side scrollers, so you do have top-down games in which different views can happen as well, but I'll show this. So the default view, the canonical example of default view for our course is just assignment 2, right? So the positions of the thing in the game world are the same as the positions of the things in the window space. And so, for example, when we drew the score up here in the top left, that stayed put because we're never moving the view. But if we did move the view around in this game, then the score would move as well, right? So just keep that in mind for future stuff. So the SFML default view, the window is constructed by default with that view. That's why it's called the default view. Top left is 0, 0, and the bottom right is defined by the width and the height of the window. This view doesn't move, so the entire game world has to fit into the window dimension. So if you never change the default view, then the only thing you're ever going to see is that default view. So this works for certain arcade style games or board games, for example. Like if you have a chess game or a checkers game, it's very unlikely that you'll ever need to change the view. And so if you do make a chess game at some point, or a board game like that, you can just pretty much draw it where you want on the screen, never change the view, and you'll be fine. Similar, if you play a game like Asteroids or Centipede or Pac-Man, lots of old arcade games are just defined within that one static screen that never moves. And so those are really the only type of games that you can make if you end up just using this default view. But of course, more interesting games have larger game worlds. We'll want to move the camera around, and so we'll look at this. So the simplest theoretic type of camera that we could come up with that's not the default view is called this position lock. And the position lock literally just sets the player's position as some fixed point on the screen, right? So here, for example, we see this old racing game or driving game, and what happens is we are going to center the view on this player. Now, this is not technically centered, because in this game we do have a little mini-map over here. So I'm not talking about mini-maps and stuff yet. We're gonna talk about that in a little bit. But let's pretend that part doesn't exist. And so one of the things that you can do with an SFML view is called set center, right? And so if you set the center at the player's position, you will get one of these position locked cameras. Really, really easy. And like the video we just watched, this is best when the character is really small in comparison to the view. Why is that? Well, because even in my opinion, at this scale, with the character that small, it's still a bit jarring, right? Like you kind of get motion sick with the whole map moving all the time. And so just keep in mind that this position lock, it's good in certain contexts, but not in all contexts. Now, going forward, any of the views that we're going to talk about can have something called camera smoothing applied to it. So over here, there's really no camera smoothing. It's just literally every frame of the game, set the center of the view to the player, right? But maybe we want to smooth that a little bit. So any of these techniques can employ different camera movement techniques as well. By movement, I mean when we set the view, do we want it to immediately go to that, or do we want some sort of smooth transition where the camera moves toward the position that we want to? So we can talk about this like auto lock thing where the camera's instantly on the target, or we could also talk about some sort of smoothing where the camera glides toward the target. And so you can choose which fits your game best. So if we look, who knows this game? Who's played a lot of this game before? Anyone? Terraria? Yep. So in Terraria, you are super, super small in comparison to the camera. And so this sort of auto lock, position lock camera is just fine, right? Because the world isn't moving that much in comparison to your field of view, so you don't really get this this like motion sickness, I would say, or this disorientation from that. So if you've got a really small entity in comparison to the view, you can use this. However, you can apply some sort of smoothing to that as well. So this is another platformer called Super Meat Boy. And in this game, yes, the camera does want to be centered on the player, but you can see this effect of smoothing. So the player has some speed, right? But the camera also has a speed. And so when we move the camera toward the player, it's not just immediately setting the view. We have a little bit of mathematics there that says, okay, move the camera toward the player at a certain speed, and then when it catches up, stop moving it, right? So this is one of those examples of a position-locked camera, but we've applied some sort of smoothing to it as well. Now, so these are examples where we follow the player in the X and the Y, but of course we can follow the player in the X or the Y as well. So this is a really, really old game. I think it's just called Kung Fu, and the camera follows the player in the X-axis in this game. So this is the Super Mario Brothers, but it's not technically Super Mario Brothers. It's more like our assignment 3 in terms of the camera. And so this is just completely locked horizontally. So if the player moves in the X direction, the camera follows, but if the player moves in the Y direction, the camera does not follow. And now this game, it's a really old game, so it's got limitations. So like it goes to the next level by walking up these stairs, and then you've got another just horizontal side-scrolling type level. This could lead to, in some cases, sort of like jerky left and right movement. So every time you do move left and right, the entire game world moves. If you want that to happen, that's fine. If you don't want that to happen, then you could apply some sort of smoothing to this as well. So just because we don't show an example of smoothing here doesn't mean that you couldn't also apply smoothing to this camera. So it's useful in these types of games, like in assignment 3, where we don't go higher than the screen, right? So just this view just moves in the X direction. Similar to X or Y position lock-on, we could also have a system which follows in a particular line or on a curve or whatever, right? So over here, this Adventure Island / Wonder Boy type camera, the player is actually going like down and to the right. And so in that case, we are following horizontally, but on this sort of slope, right? So all of these types of locking can have more advanced mathematics in it. And over here, we've got this sort of 2.5D game, which means that like the world is rendered in 3 dimensions, but the player can actually only move in 2 dimensions. So in that one, we've got this sort of spiral in 3D space, and we've got a camera that's locked to like viewing the outside of that cylinder. So that's just like directional based scrolling. So it's a type of lock-on, but it's following a path that's more complicated than just a simple 2-dimensional line. Okay, I'll take your word for it. I'm not sure of the names of all of the games. The article, though, would have the names of all the games, so please go read that. Next, we have this simple box or trap view, which the video talked about. And this is actually like a great thing if you make a side scroller in which you move both horizontally and vertically, then this box or trap view is great because, as you saw in the video, it limits the amount of camera scrolling while simultaneously making sure that the player in that game is visible at all times, right? So you define some sort of box around the player, like up here, I can't remember this game, this is some sort of gauntlet type game down here, but you define whatever box you think works for your game, right? So up here, it's a simple box that's centered on the center of the screen, and whether or not this works for your game is completely up to you as the game designer. What you would probably do in practice is define some box, do a bunch of gameplay testing, say, okay, that worked in some areas, maybe not in other areas, and then you change that as a sort of iterative process of game development. And so the view is only going to move if the player tries to leave that box, right? And so this is useful for games with a lot of jerky back and forth motion, or like if you're some fighting games or games where you're fighting lots of enemies, etc., like this gauntlet type game. So here you can see that if the camera only scrolls up if the player is hitting the top of the box. It only scrolls down if they're hitting the bottom of the box. Same thing with left and right. However, down here in the gauntlet game, the box is sort of off center. So why would you make the box off center? Well, again, that's a gameplay decision. So up in the Gauntlet game, you can see, okay, the player is probably starting really high in the level to the left and wanting to go to the right and down. So by offsetting the box up and to the left, what we're doing is we're giving the player more foresight to things that are happening to the right of the player and things that are happening below the player, right? So you can see here, the player, as it moves to the right, it's got at least half of the screen of information of enemies that are coming toward it, same with the bottom. But if the player does have to backtrack a little bit, it's probably the case that there's not a lot of enemies there, and so you can go further to the left on the screen than you can on the right. So it's really interesting. Like, I don't know, this sort of thing fascinates me in terms of like user interface design. It's not really like a user interface that you're interacting with, but it is a user interface into the game in terms of, okay, what am I seeing and how does that affect gameplay? Yeah, question.
Well, I guess that's what makes the biggest difference between a 2D view and a 3D view, because when you're viewing in 3D, you can see infinitely ahead, whereas in 2D, if you're looking at it from perpendicular, you're always going to have a finite distance. That's kind of I imagine that difference probably accounts for a lot of the complexity of 2D cameras as opposed to 3D ones.
Yeah, so I'll just repeat a bit of that because it's hard to pick it up sometimes. So it was more of a comment than a question, but it's saying that, yeah, the 3D cameras, if you are looking in a direction, you can see sort of infinitely in that direction, right? So if you're behind Mario looking over Mario's shoulder, you can see everything that Mario can see for, well, you know, we say infinite, but it's like whatever the draw distance of the game, whatever the hardware allows, versus a 2D game. I should make a slide about that. That's a really good point that I hadn't thought about. A 2D view is by nature going to give us some limited view of this possibly infinite two-dimensional world. Here we've got another example of a box trap, and this is from the game Fez, where it's another, like, I don't know, what would you call this, like a 2.75D or whatever, you know, it wants to call this, where it is a 3D world, but you are only interacting with it at any given moment in a 2D way, and then you can sort of switch. It's a really, really interesting game mechanic. If you haven't played this game, I recommend it. And so this box, it's a 2D box trap with only 3 sides in a 3D world that you can only interact with in 2 dimensions. Like, it's crazy how deep this can go, right? So that's neat. Now, there was position locking, but there's this other idea of position snapping. So it follows the character in a particular axis, or both axes, but here we've got an example of one axis. So in the x-axis, the camera is always just locking onto the player. So that's that sort of follow and locking camera. But in the other axis, what it's doing is this sort of catching up snapping rather than just following the player. And so it snaps the position if the character changes position in the other axis. And what this does, is it makes for smoother overall camera movement. And so you can jump and the camera will follow you, but it's not as jarring as it would be if you were locked in both directions, right? So this is almost a case of that smoothing type of motion applied to this camera, but only in one direction. Another example where it's not necessarily locking onto the player, but it's locking onto the platforms in the game, right? So here in Super Mario World, it's like position snapping, but it occurs based on sort of logic based on the game world instead of the player's position. So you might think of this as, okay, whenever we detect that the player has landed, then we will snap to that position in that particular direction. And so it only snaps the view when the player lands on a particular platform. And this can happen in multiple different ways, right? So here we've got this platform where I think this is Rayman, and so you can actually walk like smoothly up different platforms like this. The GIF cuts off a bit soon, but you can see that this is the case as well. And apparently in this version, what happens is so the camera is like snapping up toward the player, but if you jump before the camera has fully snapped, then it doesn't keep going. So there's all sorts of ways that you can do this. We talked about box traps in which there are actually like boxes around the player, but we can sort of take that idea and apply like an arbitrary amount of complexity to that by defining camera zones. Oh, we've got some sirens outside. I'll just wait for that. So these zones, instead of just being a simple box, can have an arbitrary geometry, right? So here in Super Mario Brothers, we do have this camera zone. And what this camera zone is that if I am a sufficient amount of distance to the right, then the camera will follow me to the right. But if I am to the left of that, it will not follow me until I have gotten to it, but it will start following me when the player crosses this line, right? So you can sort of see what's happening here. As the player goes back to the left and then crosses that first line, it starts to smoothly follow the player until it gets to the middle line, and then it locks onto that, okay? So we can speed up or stop the camera based on the direction of movement and location within that camera zone. And these can get sort of arbitrarily complex, as I said. So over here, this is a pretty simple example, and this is based on sort of the level geometry. So this is from Metroid for the NES. So if you're in a purely horizontal part of the game, then this camera zone may only define a zone in the horizontal, or if you're in a vertical part of the game, then it will define one of these boxes in vertical. Super Mario World, oh my god, what's going on here? I won't even attempt to explain all the things that are going on here, but because Super Mario World, unlike Super Mario Brothers, lets you go back and forth, left and right in the level, then if I'm moving to the right or to the left, what I actually want is, so if I'm moving to the right, I want the player to see, well, regardless of the direction that it's moving, I want you to see more than half of the screen in that direction. So I've got one thing over here on the left, which defines the following if I'm moving to the right from to the right of this position. And the opposite is if I'm moving to the left from the left of this position, it will follow at this level. But the camera will start moving if you're in a... If you happen to be in a part of the level where you're to the left of those things because it's like a wall or something, then the camera will start moving if you are to the side of this or to the side of this, right? So these can be like arbitrarily complex. I think the camera in Super Mario World is one of the best cameras in any 2D game ever. So I would recommend maybe trying to implement something like this if you're making a platformer game for your project. We've got other camera zones. So over here, this is very much like what we just talked about. So this is an old arcade game. I forget the name of it. My uncle would kill me because he actually has this arcade game in his house. I forget the name of it. It's a very, very difficult game. But you can see as we're moving to the left, the camera snaps to one part of the screen. As we're moving to the right, it snaps to another. And this is very similar up here, except we also combine that with platform snapping, right? So any of these things could also, any of the things we're talking about can be combined together to have multiple different effects in the game. Not only can we move the camera, but we can also define the zoom level of the camera, right? So again, if this was an actual camera, this would be sort of the focal length of the camera. So over here in this game, if you're fighting Bowser or you're fighting some boss, maybe you want, okay, I want the player and the boss to be as big as possible, but I want them both to always be on the screen, right? So if Bowser's moving around or if you're moving around, you've got to be able to shoot this stuff at the boss. And so I want the camera to zoom out if the thing I want to be on the screen moves too far away from the player, right? And you can calculate this rectangle pretty easily and do that in your game as well. Over here, there's this sort of idea of camera focusing, which means that, okay, yeah, for most of the game, we want the camera to be focused and following on the player, but like this, and like the example I showed before with the treasure chest, sometimes you may want the camera to sort of go away from the player, to show them something interesting that may be just out of view. So here, there's something interesting that happens in the game. I'm not sure exactly what this is, but the camera actually does focus. And my God, the different parameters here with the camera, I'm not even going to attempt to describe what's happening there with that camera. So over here, that can be described as a camera window, and this camera window can shrink and grow as the players start to get further apart. So a lot of fighting games do this, like Street Fighter, Tekken, 3D fighting games especially. You know, you want the players to be as big as possible on the screen, And then as they move apart, because strategically you might want to be farther away from your opponent at some point, or maybe they throw a fireball, it knocks you way back, then this camera window would grow, and you would, to a point, shrink the players in the view so you can see them, and then they move back together and the camera view goes in again. So it's very useful in games when you want to ensure that some things in the game world are always visible on the screen. But the interesting thing here for fighting games is that it also affects the camera. The game mechanics affect the camera, right? Because we want both players to be on the screen. But the camera also affects the game mechanics, because there should be a maximum size of the game world that we can see, because we don't want the characters to get too small. And so at a certain point, when the characters get too far apart so that they would be too small on the screen, we actually limit their movement to the size of the view. So it's really interesting how this, like, it goes both ways. Yep.
This is different from the camera trapping thing. There's a trapping box type of camera, right?
Yeah, so the question was, how is this different from the box trap? So in this one, what's happening is the movement of the camera is sort of like a camera zone or a box trap, but the size of the view is being changed based on the position of things in the game. So you're right, it is similar to a box trap in how it only moves the camera when they get to this particular region. But the thing that's changing here is the size of the view when the players get so far apart. So this isn't, I guess I should have used a better example, but in many fighting games, when the players move further apart, like, they will shrink, like they will zoom out so that the players can move further. So I'll get a better example of that for the future. Thank you. You can also do cool things with the camera, like shake the camera if there's some sort of earthquake or thing. So over here in the original Super Mario, so this is the first game that second game that Mario appeared in. Does anyone know the first game that Mario appeared in? Yeah, Donkey Kong. So this was Mario's first standalone game. Whenever you hit the POW here, they want to convey the idea that hitting this POW affects things on the screen. How would you convey this powerful effect? Well, I'm going to have some sort of camera shake. Over here, you have a similar sort of camera shake event when this big heavy enemy is landing and stuff. So you can do all sorts of cool camera shakes. So go nuts with the camera views in your game. I think it makes it really interesting. And it literally takes a boring game and makes it interesting. It's actually insane how much the effect of the camera has on the game. Here we have a portion of the map from the original Legend of Zelda. Yeah, I know, I'm old, but like, it's a good example, right? So here we've got this complete game world that we want to be able, the player, to move around in. So would we just show the whole game world, right? And have the player move around super tiny? No. Would we center the camera on the player and just follow them around? Probably not. So what this does is we define a sort of grid of grids in the game, right? So we've got this sort of room view. So when the player is inside this room, let's just call it a room, or we'll call it a grid cell or whatever. When the player is inside this room, we want to show that entire region. And then when the player goes to another region, we show another region. So if the player is within this rectangle, our view is set to that rectangle. If the player is within this rectangle, we set to that rectangle, right? So you could have an arbitrary area that you want to show, but it should have something to do with the game mechanics. And this is what we'll be doing in assignment 4. So a view can be constructed in 2 different ways. So the first way up here is we define a rectangle. And that rectangle has the top left X and the top left Y and the width and the height. Or we could specify those with 2 different vectors. So we could have the the second way is actually different from the first way. If you specify it in the second way, this actually defines the center position of the camera and the width and the height. So if you want to define it by the top left, you can use the rectangle way. If you want to define it by the center, then you would specify the center point and the width and the height. And depending on, so for example, if you're doing this sort of view, maybe you would want to define this by the top left, maybe the math works out. But if you want to center the camera on the player, maybe defining it by the center is easier. So this means that the same resulting view can be accomplished in multiple different ways. And I have a slide coming up that shows this, but this would accomplish the same different view by specifying the top left or the center. So of course, to get the center from the top left, you would just add half the width and half the height to the top left. So using the top left or the center may be more convenient based on the game that you're making. So here's a little diagram of this. Here, for example, is how we would specify this view with the X and the Y and the width and the height. And so in our assignment 4, this is exactly what we will be doing. We will be figuring out, so I'll tell you, okay, a room of the game is going to be so many tiles wide and so many tiles high. You will have to do the math to figure out which of those rooms or areas that the player is actually in right now, and then specify the view by either the X and Y, the width and the height, or by the center X and the center Y and the width and the height. Okay? And so there are going to be 2 views in assignment 4. One is the room view and one is a follow camera. So if you want to do the follow camera, that's the easiest thing in the world. You literally just get the player's position and you set the center of that, but you still have to set the width and the height of that camera. And the view can also be zoomed toward the player or away from the player if you want to. So maybe you have some cool effect. If the player picks up a new item, you could like zoom in and then zoom out or whatever on that. The view can also be rotated. This is incredibly disorienting because the view has rotated, but the controls remain the same as the game world, right? So if you rotate the camera view like this, if I hold up, the player is not going up straight like this, they are going up and to the right like that, because your controls are still controlling the player with respect to the game world, but the view could be completely arbitrary. So you could rotate the view like this. Maybe you've got some, I don't know, maybe the player gets drunk in the game or something like that, and you're like rotating the view back and forth. There's so many different cool things that you can do with the cameras and views that are not obvious. Okay, viewports. So views define which part of the game world will be drawn to the window. You know all of that by now. But a viewports, they define where on the window that the view of the world will be drawn. And you may not, okay, I've got examples of this. So for example, you could say, I only want the left half of the screen to be used to draw the game world, right? Maybe I want the right half of the screen to draw this other thing, like my inventory that's constantly up on the screen or something like that. So a viewport is which part of the window will be used to draw this view. And so by default, the default viewport is the entire window, okay? So the window is not the window. The viewport is the window, right? So over there, like if I have the actual window, the view would be sort of the size of the window, and then the viewport would be like where on the wall the window would be placed. So the viewport, it's a little bit confusing at first, but it's actually a much better system, is that it is not defined in pixels, but it is defined as a ratio of the window size, which actually when you're talking about viewports makes a lot more sense. So the viewport is set as a part of the view. So the view, again, that is the window into the world. So we can take the view and then call .setViewport, and that will be a float rect. But XY is the ratio of the window where we want the top left to be, and width and height is the ratio of the window of the width and height. So what does that mean? Let's look at an example. So if we took a float rect of 0.25, 0.25, and then 0.5 and 0.5. Okay, let me get my little marker out here. So this is with respect to the window size. So 0.25 in the X is 1/4 of the window size. 0.25 in the Y is 1/4 of the window size. So this says the viewport, the part of the window that I want to use to draw this view, is going to start at 1/4 across and 1/4 down. Then the width and height over here are 0.5 and 0.5. and that is half the size of the window. So I want this to have a width of half the size of the window, and I want this to have a height of half the size of the window, right? So that's how the viewport is described. It may be possible to define it in pixels, I'm sure, but by default, the way that you describe it is by a ratio between 0 and 1, where that's just multiplied by 100 to get the percentage, etc. So how do we use a viewport? Why is it useful? You could do a 2-player split screen in your game if you wanted to. I don't know if any of you are old enough to have actually played a 2-player game on the same game console on the same TV, but like I remember like playing GoldenEye on the N64, and it was so competitive that we would like have one person, we would tape a blanket to the screen, and like my friend would be under the blanket, only looking at the bottom of the screen so that they couldn't look at my part of the screen to see like where I was or what like health I had and stuff, right? So this is how you can accomplish that, is with these viewports. So for example, if you want the player 1 view, so that maybe is just centered on player 1, and if you want player 2 to be centered on player 2, you could have player 1 be, okay, that is 0.0, so 0, 0. So player 1 is going to start in the top left corner and go half the way over and all the way down. So you could have split screen be horizontal or vertical, right? So in this way, we've done it horizontally. So it starts up here at 0, 0, goes across 0.5, and the height is 1. And then the second player's view starts at x 0.5, y 0. That's half the way over, but still at the top, and then has the same width and the same height. So if we go back, is that the same? Yes, it is. All right, so, or what you could do is create maybe a mini-map view. So if you have a view, which is defining a view of maybe the whole level, right? And then you could stick that in a viewport in your game, up in the top corner or down in the bottom corner, and then maybe have like a little blinking light where the entity is, right? So you can have a mini-map view, and it would be cool if you had a mini-map view or something like equivalent to that in your final project. That was one of the suggestions that I had. So viewports can be used to create really interesting and useful views for gameplay, and it's cool because that's one of the things that we want this library to do, right? We just have a view, we have a viewport. I'm sure that you could all do the math yourselves to actually draw those pixels to the screen, but it's good that the rendering library has that done for us. You could have in-game minimap, a rear view mirror. So if you're doing like a driving game, yes, there are 2D driving games. And if you want to be able to see behind you, you could have a little viewport where you're rendering sort of what you think is behind the player. You could have an enemy's perspective. So if there's some enemy that you're trying to hunt in the game, maybe you pick up a power-up that lets you see where the enemy is in the game. And while that power-up is active, now you have like a split screen, you can see that enemy walking around, or maybe it would center on some treasure or something like that. There are so many really interesting things that you could do with this. So, okay, we've got these camera types, we've got these views. How would we actually implement that in our game engine now that we have this idea? So there's two main different ways that this is sort of done in game engines. And the first one is going to be, okay, I've got some sort of variable which defines the type of camera that I want to do. So for example, a bunch of different camera types could be defined within an enum as an integer, or it could be a string, the type of camera that we want to look at. Or we could do something more of the object-oriented programming sort of way, where we would actually have a camera class, and then that is sort of done in the game engine. So that's more of the 3D game way of doing it, versus this way, which I want us to do in our game engine, because it goes along with the whole ECS way of doing it. So we're going to have a camera system, and then up here, we are going to have whatever different types of cameras that we have, and down here in the camera system, we would just say, hey, if the current camera type that I'm using is the follow XY or the box or the Zelda rooms or whatever, then I would get the view, set that to the screen, etc. So that's one way of doing it. It is not the right way of doing it. It just happens to be the way that our game engine is going to do it. Otherwise, you could have this idea of, okay, I've got a camera class, and this has an update method, and that's going to affect the camera, etc. This would be more of the object-oriented programming way of doing it. Alrighty. The sort of last thing that I want to talk about is this idea of parallax. Has anyone heard of parallax effects before in 2D games? Okay. So parallax is a way of implementing depth or a 3D feel into a two-dimensional game, and this is one of the things that you should have to do on your, or you're going to have to do on your project. So I'm going to play this video now. I'm going to turn the sound up, which means it's probably going to be like air blastingly loud on the recording, but I'll fix that in post when I edit the video. But I'm going to play this video for just a few minutes, but please go back and watch the whole video. But it's going to explain what parallax is, because it's very difficult to explain parallax without a nice animation. And rather than just like spend a whole bunch of time creating my own animation, well, I could just play this, right? Okay, so I won't play the whole video, but you get the idea now of what parallax is. Please go watch that whole video, because it's a great video, and I hope it gives you some ideas for the project. I'm not going to lecture on like the mathematics of parallax, because it's basically just taking some other layer in its most basic form, like you said, and moving that at a slightly different speed, so that it either conveys it conveys that something is far away, and something he was about to get into, but I didn't want to play it too long, is that you can have foreground parallax as well. You can have things that actually move faster in front of the player, like some grass in front of this or whatever, in order to convey parallax. So that's it for today. Please make sure to go back and have a look at those videos. I don't want to call it homework. I'm not grading you on it, but you know, ideally you're interested in this sort of thing and you want more information. Also, please keep in mind the due date of the, it's a week from now for the proposal, right? So it's only 1 week away. If you have not found a partner, or sorry, not partner, but like group mates for the project, look around. Maybe, is anyone here looking for people for the project? The people who come to class are always sort of, you know, on the ball. So if you do need people, please like post on the Discord LFG channel, post in the general channel, just get that project, get the proposal done, make sure you're not slacking. Don't save that till the day before, because you might not be able to find anybody, right? So just make sure you're on top of the project stuff, because worst case scenario, you might be alone at the time of the proposal, and then I'll have to get involved and like put you somewhere, and that's never fun. So I think what I'll do is I'll actually post on D2L, and I'll say anyone who cannot find partners for the project, send me an email, and then maybe by like, you know, Friday or something, or tomorrow or the weekend, I'll just put people in groups randomly if they can't find anybody. But make sure that please don't leave it any later than this weekend. If you're absolutely desperate, send me an email and I'll try and help you out as much as I can. Thanks.